Okay, we did run into some issues yesterday. I apologize for that. The guys worked on it yesterday afternoon and last evening. I talked to them this morning. They said they fixed most of those. So I think I have your email addresses. I'm not certain though. So I might pass a piece of paper out and get your name and your email, and I'll send you a patch probably tomorrow or the next day. I've tried to get it out of them today, but they said they didn't go through testing yet. There was a bad DLL that was causing most of those issues there. So I apologize for that. Also, even if you don't own the software, we're going to give you a free technical support for the next 30 days. So just call us up and we'll be glad to assist you on any projects you guys are working on. We do that normally as well, so we don't charge for our technical support. And a couple people, guys and gals, ran into some weird issues, and they tried to reproduce that last night, where you could not cut contours off or cut cross sections off of contours, or you couldn't generate contours. If you can contact us, call our phone number or something, and talk to one of our support engineers. We got to figure out what's exactly causing that. They thought maybe there's some other software installed on your computer that's maybe conflicting with it, or something else going on. So we weren't certain exactly what was causing that. But anyways, I talked to them this morning and they promised me they'd have it fixed. So I'll try to get that turned around. Two other things I forgot yesterday. We were going to do bridge scour, so we forgot to go over that. And so today we're going to focus mostly on 2D stuff and on any projects you guys want to work on. And I can show you some projects I've worked on as well. And also we forgot to do floodway analysis. So how important is doing floodway computations here? Pretty much everybody. Okay. Is there anything else you guys want to cover besides the 2D stuff? If you think of it, we covered the dam failure analysis yesterday. That was pretty simple, right? You can also do a dam break analysis with 2D modeling, although it's a little bit more complicated. So let's go ahead and see if I can do that bridge scour stuff. We did that study yesterday, so let me try it. So maybe watch my screen first, and then you guys try it on your project, right? You guys all did that bridge project yesterday. So let me go see if I can find that one. So let me go in my folder, under training examples, bridge project. Let me see if I open this guy up. So, oops, wrong file. So let me grab the other one. Go open that one up. There we go. That's a bridge we had yesterday, right? And someone was complaining about not following the contours. The problem with it is it's following the grid, and what's happening is it's smoothing those contours out. This grid resolution is 8 feet by 8 feet, 8 by 11 feet. So that's part of the problem, is it's not following those contours because it smoothed those contours, and in reality it's trying to follow that grid. And then it smooths that edge of that line, so it gets a little different. The other thing is, someone reported that it filled in this area here. And what caused that, if I go over to my results, go to flood map, in here's an option for filling that area. I'm trying to remember where it is. I think it's right here. So remove ponded areas and holes less than or equal to 10,000 square feet. So if you change that value down lower, this hole over here that you see in my original model or in my training course, that hole will show up again. So you can change that option, turn that off. Either turn it off or lower that value. And then someone asked yesterday, they wanted to go and clip out some buildings. So if you create a polygon layer in GIS and use that, you can clip out those buildings using this option there. And I could demonstrate that real quick. We'll go back over to the first project I did yesterday. So let me go find that. It was for the city of Akron. And let me just see if I have that model here. There it is, flood analysis. Hopefully it has all my data in it. I don't remember if I saved it, so we'll see. Sure enough. So there's my model from yesterday. Remember that? So, in fact, that'd probably be a good one to do scour analysis on, right? So we can go look at our existing bridge, that one. But we did have some structures here, right? We had some buildings. I'll turn the buildings back on so we can see them. You see all those structures there? And when we generated our flood map, of course, it covered up those buildings. So if we go generate that flood map again, if we go to results, go to flood map, and I want to look at my 100-year storm, and I think everything should be good. I'm not going to turn on the buildings yet, so we'll leave that off. And just hit OK. It's going to recalculate our flood map. And we can see our flood map in there, but if I turn off the buildings, right, if I unclip the buildings here, you can see it's covering up where the buildings are. So I might want to crop where the buildings are. So what we'll do is we'll go ahead and leave the buildings turned off. I could turn them on again, but we're going to go over to our flood map option. Options here, our flood map command options. We'll go ahead and clip out any buildings that, and notice it looks through the list of layers looking for a word like building or structure or whatever, and it tries to guess at what name that is. And then I'm going to turn this option off, so those holes, otherwise it's going to fill up all these holes here. Hit OK. Hit OK again. It's going to recalculate that for us and should clip that for us. See, so now you can see these holes are put in your model. So there's some additional options there. If there's things that we're not doing though, let us know, because someone had mentioned something yesterday to improve the program, and that's something that I had never thought of, and a kind of unique idea. So if, as you're working with the software, just use this as a sounding board. Most of the stuff you see in the software actually came from users like yourself saying, this product's pretty good, but you could improve it some. And so we definitely appreciate that. Well, let's go and do a scour analysis on this, right? We have this bridge down here, and you can then try it on your bridge. So we're going to go and look at that for the 100-year storm, see what happens for that bridge structure. So to actually calculate scour, I have to have a velocity distribution through the bridge opening, or I can't tell exactly what the velocities are around those bridge piers and the abutments. So if I go and look at that structure in our cross-section plot, right now you see it's a solid color. If I go to options and I turn on velocity distribution, turn that option on, it's just colored as one color. That tells me I haven't computed the velocity distribution. So there's a specific command or specific instructions we have to give HEC RAS to calculate that. So there's different types of scour. There's abutment scour, that's around the abutment. There's pier scour, and then there's contraction scour. In fact, I have a PowerPoint that demonstrates that. Let me see if I can find that quick. So we'll go over that into my courses here. Let me see if I can find where that one is. Trying to remember which one. I think it's advanced bridge modeling. Let me take a look at this. All right, so we want to go, yeah, so there we go. So let's go over this. All right, so we'll look at bridge scour. So scour is probably the most important cause of, or main cause of bridge failures. So from analysis here, it says 60% of bridge failures are from scour. So what's happening is usually the piers, the foundations or the piles for the piers are eroding away, and the pier becomes unstable, like you see here, and the bridge fails because of that. So as the water contracts through that opening, it speeds up. So there's a document called HEC 18. It's published by the Federal Highways. It's no relationship with the Army Corps HEC Center. This stands for Hydraulic Engineering Circular 18. And they talk about the different types of scour. There's contraction scour, pier scour, and abutment scour. We'll go over that in this presentation. So based on the bridge skew, the pier shape, and the abutments, that can change the amount of scour that occurs at a structure. So, and HEC RAS only computes the scour at one bridge opening. So if you have a multiple bridge opening, you actually have to break the model up So you have to analyze each bridge separately. And the way you do that is you have to close one off, model that, and reduce the amount of flow so it's going through the one bridge as you compute it through your multiple bridge opening, and then analyze the other one the same way. So first thing we're looking at is contraction scour. So as the flow contracts through that opening, it's going to speed up. And so there's two types of scour that occur. And again, the mechanics of that scour is pretty sophisticated, so they develop empirical equations to kind of predict that. And based on, you either have sandy soil or you have clay soils, and that can have a different effect in there. Usually clay soils just take longer, and usually the same amount of scour occurs over a long period of time. But anyways, there's something called clear water scour. It's basically assuming that the water upstream of it has got no sediment in it. There's no suspended sediment. And then there's live bed scour, which actually has sediment in that. So there's two equations that are used for predicting that. And you got to be careful of these equations. They give you kind of an estimate, but sometimes they can get unrealistic. So I have this description here. I'm going to just read it because there's too much text to kind of summarize it. So significant scour, contraction scour can occur if the overbank flows, the portion of the high flow above and outside the banks of the main channel are captured by the roadway approach embankments and forced through the bridge opening. So that makes a lot of sense, right? So if we got a lot of flow on the overbanks, as the flow contracts through that bridge opening, it's going to speed up quite significantly, and that will cause quite a bit of scour. Flow through relief bridges or approaching roadway embankments can reduce that flow and the contraction scour. So if we have a place where water can divert itself, obviously it reduces the amount of water that's flowing through the main bridge opening. Deep contraction scour can occur also in the relief bridges located in the overbanks. Again, you can't analyze that directly with HEC RAS. You'd have to break that model up into pieces and analyze each one separately. If there's no overbank flow, only a change in the effective main channel width, including the bridge piers and the flow, that will influence the live bed contraction scour. Large substructure elements like piers, pile caps, pile groups can increase contraction scour significantly. Basically, it creates a pressure flow underneath there and speeds up that flow again, kind of like flowing through an orifice. You would think of it like if you punched a hole in a milk jug. You're going to have a lot of velocity on that. Submergence of the bridge superstructure can cause pressure flow. You get what they call vertical contraction scour, and that increases your scour pretty dramatically. Okay, next thing we're looking at is pier scour. So there's two types of scour that it can occur. There's a wake vortex and a horseshoe vortex that occurs. So pier scour occurs due to the acceleration of flow around the pier and the formation of these flow vortices, known as a horseshoe vortex. So the water kind of tumbles on itself as it goes through there and digs up behind that, along the edge of it. Then the horseshoe vortex removes the material from the base of the pier, creating a scour hole. As the depth of that scour increases, the magnitude of the horseshoe vortex decreases. So it kind of gets reduced by that, thereby reducing the rate that material gets removed from that scour hole. Eventually you get to a point of equilibrium between the bed material being withdrawn and deposited, and basically the scour hole stops growing. So if we look at that in more detail, the width of the pier has a direct effect on the depth of scour. That would be kind of obvious, right? Wider piers produce deeper scour than narrow piers under the same conditions. The maximum expected pier scour depth ranges between 2.4 and 3 times the pier width for circular or round nose piers aligned with the flow. Now, circular piers are almost always aligned, right? I don't know how you would have it not aligned. The length of the pier has no appreciable effect on the scour if the pier is aligned with the flow. So if we have a circular columns with structure between them, kind of support that, that won't have any impact on that. The length of the pier has no appreciable effect on there. But if you change the angle of attack, then that basically widens the the amount of scour. It widens the effective width of the bridge pier and has a big effect on your scour. The velocity of the approaching flow increases the scour depth. Faster flow produces deeper scour. Fine streambed sediments, silt and clay, have scour depths as deep as sandbed depths, scour, even if bonded by cohesion. The effect of that cohesion, though, clay particles, if you know, they kind of stick together. There's a ionic bond between the particles that basically increases the amount of time to reach that point of equilibrium. So what you'll notice at a bridge is when you go out to measure it, there you won't find the scour hole, right? The scour hole will be filled up. But then the next time it floods, that scour hole will dig right back down again. So once you've loosened up that material around that bridge pier, it can be eroded quite quickly. So that's what happens even when you have clay soils, they'll fill up with loose sediment and non-clay materials, and then you go out and measure and you say, okay, I'm measuring the bed, and you're looking at it, you can't see any effect of that scour, but the next time a fast-moving flow comes through there, it opens up that hole again. So that's a little more difficult. So you actually have to do some core samples or sample it and see what's actually happening there to kind of figure out what's going on. So over time, that bridge becomes less and less stable due to that scour. All right. In sandbed channels, the maximum depth of scour is measured in hours. So the first time through it, it's going to erode quite quickly. Whereas cohesive stream beds, you talk about clays, silt, sandstone, even rock, it can take days, months, or even years to reach that maximum scour depth. So the shape of the pier has an effect on that scour. A streamlined upstream end reduces the strength of the horseshoe vortex, reducing the scour depth. A streamlined downstream end reduces the strength of the wake vortices. So if you remember, if we go back to that picture, we have two types of scours here. We've got our horseshoe vortex occurring here, and we've got our wake vortex that's occurring there. So it's two effects that we're trying to simulate. A square nose pier will have the maximum scour depth, about 20% larger than a sharp nose pier and 10% larger than a cylinder or round nose pier. The shape of the pier nose has no effect on the magnitude of the scour when the angle of attack is greater than 5 degrees. So if we have a skewed bridge pier, it doesn't matter what the shape is. It's going to go ahead and create the it'll be the same amount of scour. Now, although, like I said, if you have a round pier, there's no skew angle associated with that unless you have some sort of diaphragm between the two piers. Ice and debris can increase the width of piers, changing the shape of the piers and cause the flow to plunge downward against the stream bed and increase the pier scour. So something you have to analyze when you're doing bridge modeling. And so up in Canada, if you do projects, I do projects up there occasionally. They have to worry about debris a lot because they'll get a storm and logs and other stuff will be floating down. It'll basically get hung up underneath the structure, basically decrease the bridge opening and increase the velocity of flow going through that bridge pier or through the bridge opening and creating a more scour. So that's a real problem for them up there. And I would assume you probably have similar instances around here. So in HEC 18, produce further guidance on local pier scour. They say use the Colorado State University equation, but there's a new equation that was developed by Florida's DOT as an alternative for wide piers, where you have very shallow flows with fine bed material. That is not yet incorporated into HEC RAS. So if you want to analyze that, you have to go and download that document, that HEC 18 fifth edition, and do it with a spreadsheet. And you can do it quite easily. The equations are set up. In fact, you could probably search for a spreadsheet for that equation and pull it up. Last thing we're going to look at is abutment scour. So basically what happens is we've got this overbank flow, and it's going to get tightened up and go right through that channel. So there's two types of scour again. There's a horseshoe vortex again, and there's a wake vortex downstream. So local scour occurs at the bridge abutments when the abutment obstructs the flow. It's pretty obvious, right? The obstruction of the flow forms a horizontal vortex starting at the upstream end of the abutment, running along the toe of the abutment, and forms a vertical wake vortex in the downstream end. So basically what's happening is the water's tripping over itself and ends up creating a radial pattern underneath the bridge deck and starts scouring out along the abutment structure. And then downstream of it, it creates a wake vortex as it's trying to expand out and can drill down behind it. So there's two equations that are developed for that, to model that. There's one by Richardson called the higher equation, and then there's one by Dave Froelich. I went to school with Dave, so that equation was developed when he was at the USGS. So abutment scour, there's potential for lateral channel migration. So basically it can move sideways, right? So you can scour out your abutment and your bridge can move. So there you want to look at armoring. You want to go and armor that abutment so you don't have that issue. Long-term degradation, contraction scour should be considered when monitoring the abutment scour. Riprap and guide banks. Guide banks are basically kind of like wing walls or structures to kind of guide the flow through a bridge opening. They can protect that abutment from failure. So the bridge structure is pretty expensive, right? It could cost several $1 million to put in, but if you put in some sort of structure like that, it might not cost that much, maybe $10,000 or $15,000, $20,000 worth of work, maybe more than that, depending on the size of it. But that can seriously help that structure from running into that. Abutment scour can be most severe when the approach roadway embankment leading to the abutment obstructs a significant amount of overbank flow. So we're basically saying if you have, during a flood condition, if you have a lot of flow in the overbanks, that's got to go somewhere, and if the only place it can go through is that bridge opening, you're going to have significant abutment scour at that structure. Scour can occur along the upstream portion of the abutment due to the horizontal vortex and at the downstream end of the abutment as the flow expands through the bridge opening. Abutment scour will increase if the abutment or embankment is skewed in an upstream direction. So if the bridge structure and the roadway embankment is skewed, that can cause a change in the scour equations. Basically, the one that's the trailing edge, you get scouring, and then on the leading edge on the other side, you get scouring. But it actually increases the amount of scour that occurs. The other thing it does is it basically effectively reduces the bridge opening. So a lot of people will measure the bridge opening along the roadway, but that's not perpendicular to the flow. So when they're running their analysis, they think they have a 100-foot wide bridge, let's say, for example, but they have a 20-degree angle in there, so you got to run the cosine of 20 on that to apply that, and they end up with like an 80-foot bridge opening instead, according to what the water sees. So you have to be aware of that. And I didn't talk about how to put in a bridge pier or bridge pier scour, or I'm sorry, bridge pier angles or bridge angles. So I'll talk about that here in a minute. Okay, so abutment scouring can increase if the abutment or embankment is skewed in the upstream direction. We talked about that. Abutment scour will decrease if the abutment embankment is skewed in a downstream direction away from the flow. This one is important. Vertical wall abutments. So basically you have a vertical abutment. That means basically at the bridge opening that you have vertical walls occurring there. That will cause more scour than if you have sloping abutments. Okay? Because what's happening is that if we go look at this picture again, if I have a vertical abutment here, what's happening is that wake vortex can drill right down. If it's sloping, that wake vortex has a difficult time doing that because it's fighting that slope of that abutment and can't grab a hold. So vertical abutments have quite a bit, I think it's quite a bit more than that. I think I maybe give you a number. So we'll get some pictures here. So this one is in California. It's a while back. But they basically lined the bed with concrete, which worked fine, but the problem is that it eroded downstream of that bed, and just the concrete fell away from that. So the bridge piers are still there, but you can see it's starting to erode downstream of that. Then this is actually this bridge was still open, and cars are driving through it. So in this case, the bridge piers failed just because the amount of sediment coming through there broke them off. So that's quite a bit of load that's coming through there. If you go out and stand in a flood, and if the water is flowing at 6 feet per second, which is pretty fast, and it's up to your kneecap, you cannot stand in it. It'll knock you over. That's how fast just plain water will be causing that. Of course, you could go to the beach. I don't know if you have an ocean here, but if you go into the ocean, you try to stand up, and the water waves will knock you right over. So if you have a sediment load in there, that's basically mud flow, that'll knock those bridge piers right off. So in this case, it just tore them off, and you can see the actual bridge is kind of bending down in there.
Which state is that?
California. So this is up in Canada, and here's a case where they had a spring thaw, and a lot of debris came down, and just because of the debris that got plugged up inside that bridge opening took out that deck. And you can see they put in piers to try to handle that. They put in a sharp edge pier there to kind of break up that debris, but still, if you don't get out there fast enough with an excavator and start pulling that stuff out, you can have some issues there. Here's one where you can see it scoured away. You can took it right down to the pile cap. You can hard to see, but you can see the pile cap underneath it, and I'm sorry, you see the piles underneath it, and it's filled up with debris, right? It's filled up with a bunch of stuff. They got to go back in there and fill that in and repair that. Here's another one where they got caissons. I don't know what they're doing out there with shovels there, if they're trying to fix that, but trying to fix that up. Here, this was a California DOT engineer. I don't think I would want to be out there with a beer can in my hand holding up that bridge deck, right, with my hard hat.
Could be Pepsi.
Yeah, I don't think that would be something you want on Facebook or something like that. So here you see a case where you have abutment scour. So this was abutment scour here. You can see that's rock, right? And it took all that rock out of there. So it can cause quite a bit of effect. Here the same thing is where they had some geotextile in there to kind of retain that, but the salesman will tell you, sure, it'll hold up, but you can in practice it maybe doesn't, right? And this has got sloping abutments in there, so you can see it sloping in there, but it took all that out. This is from New Jersey. They have a very active bridge inspection program. They come by and inspect every 30 years or so, because you can see how long this tree grew, right? And this pile cap has been sitting there for that long while that tree has grown to that size, right? So you can see there's quite an issue there. So if we look at computing Scour in HEC RAS, you have to basically define what they call flow distribution subsections. You're going to define HEC RAS to have little stream tubes, and it's going to look at the bridge downstream cross-section, the bridge upstream cross-section, and then the approach cross-section. Those are the only three cross-sections you have to worry about. Basically the same ones you define contraction expansion scour or contraction expansion coefficients at. So it takes and subdivides that up to a maximum of 45 subsections at each cross-section. You can't go above that. And so you could have any kind of combination. So for example, you could have 43 subsections in the channel and one in the left or right overbank. And so it depends on what scour you're trying to analyze. If you're going to have a lot of abutment scour, then you want to have more subsections in the overbanks. If you're basically worrying about pure scour, then you want to have more subsections in your channel, but you're limited to 45. Okay. And so in HEC RAS, there's a kind of a tabbed interface, and I'll show you that operates there. Basically, all the green fields are filled in by HEC RAS. That comes from either the input data or the analysis results. And the only thing you really have to define is grain size, and that's in millimeters, and you have to have a D50 sieve and a D90 or D95 sieve. And a D50 sieve, if you remember back in soils class, and I had soils, remember, at 3:30 in the afternoon, and I was just dead tired by 3:30, so I kept falling asleep in that class, and it was hard to stay awake in soils. But anyways, remember the sieve bed, you put these different size sieves on them, you put the dirt on top, and it would shake on a shaker table, and then at the end you'd weigh each of those sieves to figure out the percentage that passed through and how much was retained in there. So 50% retained and 95 is 95 retained. So basically a 95 screen is much smaller than a D50 sieve. Okay, so the black fields are what you enter. You also have to put in the K1 coefficient, which is based on water temperature, So they've done some studies and they say that warmer water causes more scour than colder water. I don't know why, but I guess maybe that if you have clay, if it's cold, the clay is more cohesive than if it's warm, it tends to loosen up. Okay. Now it'll go and look at the equations. There's different equations that are used for those. So like here for contraction scour, we have live bed and clear water equations. It'll look at both and then choose the larger one that controls. But sometimes you get ridiculous numbers, so you have to kind of be careful what you look at there. All right, so here's your K1 coefficient. Again, basically all you have to do is change your water temperature. Assume 60 degrees Fahrenheit. And then you define your pier scour, and basically defining your pier shape and the angle, if it's skewed to the flow or not. And everything else is basically filled in for you. And there's two sets of equations, one by Dave Froelich and the Colorado State University equation, but they don't recommend the Froelich equation because it doesn't seem to hold up in practice that much. It's used for specific conditions, so you have to read the documentation and see what conditions it applies for. Basically, he did that equation for the Missouri River. So if you've got a river the size of the Missouri, then that equation is probably good to use, but otherwise most bridges are not that sized. Then abutment scour. Again, there's two sets of equations. Again, it'll go ahead and choose which one controls. There's one by Froelich and then that higher one by Richardson. And basically the key things here is you have to put in if it's a spill through abutment, meaning that you have sloping abutments on there, or if they're vertical. And now vertical causes more scour. And we can take a look at that. And then if there's an angle associated with that. So by default, it's 90 degrees, so it's saying it's perpendicular to the flow. I've seen though the abutment scour equation gets a little carried away there, so I'm sometimes concerned about that because you'll get scour holes that are unrealistic. Okay, so we can look at our output. So it'll generate, when it acts nicely, it generates a nice plot for you in there, and then it also creates a little report for you. And I think that's it for my, scour prevention. Let's look at how to prevent that scour, right? So I'm not a soil mechanic guy, so I'm not an expert in this field, but I'll talk about what I know, all right? So first thing is to eliminate pier scours, don't put piers in, right? So if you can just clear span that removes any potential, any pier scour. Also reduces your construction costs sometimes because you don't have to go so deep and hit bedrock or whatever and have to worry about armoring that bridge pier. Sometimes you can't, the span is too large, right? So, or if you can increase the span between the bridge piers, you have less piers, right? And you allow a more open area for the water to flow through. Versus that one up in Canada, remember with all the debris in there, they could have probably clear spanned that if they tried, but they didn't at the time. So you can put riprap at the piers, reduce that scour. However, that basically reduces the hydraulic capacity of the bridge opening and also causes some issues where debris can get hung up. So it can cause some issues. It basically also changes the shape of the bridge pier. So you want to go and see what kind of shape you want to put in there, try to eliminate the potential for any debris to get hung in there. Put in deeper piles and footings to help strengthen the bridge pier, but that's going to raise your construction cost. You can line the river along the bottom, putting in these interlocking jacks that you see there, or sometimes they put in pavement. They'll actually go out with a asphalt paver and pave the bottom of the river. But you got to divert the river and all this other stuff that's kind of difficult at times. And again, that's only a temporary solution. You saw the instance where in California it actually eroded that away. So abutment scour countermeasures, we look at that. So riprap is the most common measure for that. So you can basically put stone around the abutments to prevent that. You can put physical additions to the bridge abutment to prevent scour, like gay-bonds or stone pitching upstream from the foundation. Sheet piles, interlocking prefab concrete blocks also help in some regard. If you can put a trapezoidal shaped channel through there, rather than vertical walls, that can significantly reduce the local scour from that. Basically provides a smoother transition through the bridge opening as that flow transfers through there. And eliminates basically any abrupt corners. And those abrupt corners are what cause turbulence, and that's causing your scour. Something you can also look at is what they call river entrainment structures. Basically, you're trying to train the water to flow through the opening nice and smoothly. And so you can put in what they call spur dikes or wing walls or barbs or groins or veins. There's different ways to kind of entrain that water to kind of flow the hydraulics through that bridge opening and reduce the amount of a contraction scour and abutment scour that's occurring there. So you usually use that at unstable streams where you might find some migration of that stream. You want to prevent that bridge from failing to do that stream migrating. So it kind of directs the flow through that opening. Again, you probably want to work with someone who's an expert in sedimentation modeling. You know, it's a complete difficult. It's a difficult field. You can get a doctorate in it. It's pretty complex. Okay. So we can also do 2D bridge modeling. Okay, so HEC 18 recommends using a 2D model for complex flow conditions. So in our model that you saw earlier, we had a pretty complex flow situation where we actually have flow coming in the one I did yesterday morning. We had a tight turn in there, so it might make sense to go and look at that from a 2D effect there. So we can account for embankments that are skewed to the flood flow. We can look at multiple openings now. When we're doing 2D analysis, we can consider wide floodplains. We can look at highly contracted flow. So when we're analyzing in 2D, we can do a much better analysis with that. Unfortunately, when you do that 2D analysis, you have to do the equations manually. You have to use a spreadsheet for that. But you can take the values out of HEC RAS and plug them in fairly easily. So we'll take a look at that. Now in HEC RAS, the Army Corps HEC RAS does not directly model bridge piers. So we put an ability to put that bridge piers in with our software, and I'll show you how that works. And HEC RAS doesn't support the bridge deck yet for bridge modeling. It assumes that we can put in the piers, but we can't assume any pressurized flow or road overflow. If you do have a bridge that kind of looks like a culvert, you can model it as a large culvert, and that's built in HEC RAS 2D. So if your bridge is rectangular, and you could basically assume those are, you know, culverts in there, and you could analyze it that way. But it's using the culvert equations through the bridge opening for that. But it's another way to at least try the problem. Okay, so some other advanced topics. I'm not going to look at this. This is for HEC RAS. Well, we could talk about it. So we didn't talk about split flows. I talked about it briefly yesterday. Remember yesterday I had this example. If we go back to this one, if I go back over here to under lateral overflow, remember I have this lateral structure over here, and I have that flow that transitions over the top. If I try to analyze that in HEC RAS, it won't reduce the amount of flow unless I tell it to optimize that. So there's a function in HEC RAS to tell it to go and analyze that split flow and determine what is diverted from that. So that's not on by default. So you're under analysis, you have to go over here to flow optimizations, and you have to turn on this optimize checkbox here, and that will then go and analyze. It'll assume that some of that water is getting diverted. When the water gets diverted, it'll reduce the amount of flow in the channel. So you have to turn that option on. Same thing for like a flow split. If you have a river where you have it splits apart, right, and maybe it combines back later downstream, or maybe it splits and gets lost or something, HEC RAS won't figure out, you know, what's going on in each of those unless you turn on this optimize, and then it'll analyze how much water is coming in on both sides of there and determine what's going on. So there we have to go ahead and look at that. All right, so there's a little checkbox for that in there. Multiple openings, we didn't talk about that either, but you can have bridge openings with multiple roadway crossings with multiple openings. You can have what they call conveyance flow areas, basically where you're assuming that water is flowing out around the structure somehow. Maybe that's a road. Obviously a road wouldn't have that kind of profile, vertical profile, but let's assume that the vertical scale is much smaller compared to our horizontal scale. And so you can see this is about 600 feet or 500 feet across here. And the vertical scale is only like 5 feet, right? So maybe a road sort of looks like that. But water would flow out over that roadway, and it wouldn't. And we're assuming that's not going to act like a weir. So if we want the software to analyze it using normal depth, don't put a roadway there. If you put a roadway in there, it's going to use a Weir equation. So if you define your roadway geometry over in this area, it will use the Weir equation. And you should only put a Weir equation if it's going to be like broad-crested Weir. Broad-crested, roadway embankment, the roadway width is probably 30 feet or maybe wider than that. As water flows up over that, that's called a broad-crested Weir. And you'd use a broad-crested Weir coefficient that's usually between 2.8 and 3.2. 2.8, 2.9 is a typical value you would use. You can look it up in our software. It's built right in there. But if you're doing a multiple opening, you could assume that, in this case, I'm not applying the Weir equation. I'm going to assume normal depth. So it's going to use Manning's equation and determine the amount of water that passes through there. Then you could have culverts. You could have some relief culverts. And you could have some bridge openings. You're limited to 10 of these structures, 10 of these items at an opening. You can't have more than that. And you kind of have to tell where the water stagnates. So you have to, upstream at the approach cross-section, which has to be far enough upstream, you define where the maximum limits are, where those stagnation points are. And the software is supposed to try to analyze where that stagnation point is between that overlap. And sometimes it's successful, but most of the times I have not had luck with that. So just be aware of that. So in a situation like this, probably would be better to analyze it with a 2D model, because it's going to analyze the water surface elevation in HEC RAS. It looks at each cross-section one at a time. One of the limitations it has is assumes that the water surface elevation is flat. And in reality, if this is quite wide, the water surface elevation across that cross-section won't be the same, right? Over in the overbank area, it might be lower, or it might be higher, depending on the Mannings and other things that are going on there. So by looking at it in a 2D analysis, you'd have a better understanding of that. So we talked about these stagnation points. So here's an example where we have water coming down. We've got a main bridge and some relief structures here, and it doesn't know where the stagnation points are, so you have to kind of it's going to try to approximate those for you, but you may have to go and have to work on that. All right, and then perched bridges are just bridges that are basically up above the ground. You got skewed bridges, and there's a little option there. And then you can have bridges that are offset, that are centric to the actual roadway crossing. So in there, you might ask, remember that video we saw yesterday by one of our guys that said, you have to define the ineffective floor. It's like 1-to-1 or 2-to-1 upstream, and 2-to-1 to 4-to-1 downstream. Well, what happens when you have a case where you have a bridge opening that's very offset to one side? In that case, you might actually have more than one cross-section defining your ineffective floor is. So you might have to put in another section here. Here would be your normal exit cross-section. Here would be your typical approach cross-section. You might have to put in some additional sections here to account for that additional ineffective flow area. Parallel bridges, typically what you do is just model them as one structure, but you could model them separately if the water expands and contracts through them significantly. But most highways, if they put in bridges, they're going to put the same structure in so that the guys constructing it don't screw it up. So try to make them the same as they install them there. And so in that case, you just model them as one structure. Okay. And dams, we talked about dams as well. We did that yesterday. We did a dam failure analysis. So let's go do a scour analysis now. Okay, so let's go back over to our other plan where we had our existing bridge structure. And we want to go on and do a scour analysis on this. So we have to do a velocity distribution analysis. So we're going to go over to analysis. And in here we're going to go to flow distribution locations. And you can define it globally, and then it applies it to every cross-section. The problem with that option, though, is if you have a very long river, let's say several miles long, it's going to slow down. So you only need to apply it at the bridge structure, downstream, upstream face, and the approach cross-section. So you could come in here, and you could come in and grab the one. So you could say, I'm going to go and pick the downstream one. So I'll come in here, I'll say, that's my downstream one. And then I'm going to grab my upstream one, click on that, and go find my approach cross-section right here, right? And so I've just got 3 of them selected, right? And then I could say how much I want in the overbanks channel and right over bank, right? So I can have a maximum 45 of them in there. So what I'll typically do is I'll put 25 in the channel, and that gives me a 10 for the overbank. So it's a good starting point. And usually that'll give me enough detail at the bridge opening. But if not, I can increase the amount of subsections in the channel and reduce the amount in there, but you can't go above 45. If you go more than 45, if I try to put in, like, say 20 here, it will complain about that. It says maximum is allowed there, and it'll set that back to 10. You have to click on the Set Values button, otherwise it doesn't do anything. So we basically have defined the information here, but you have to click on Set Values. Otherwise, if we go look at our sections down here that we're working on, down here you see they're still set to 1, right? So we're going to have to click on Set Values, and you can see it filled in the ones that we had selected in there. So it's got those defined. Or again, you could just do it globally. That's another simple way. So if you only have 5 cross sections or 10 cross sections, it won't make any difference. Software runs so quickly. Click on OK. We have to run our simulation again, or otherwise it won't have updated that. So click on the Run button. Let's go run our simulation. Okay, and it's complaining about something in there, but it does look like it ran successfully. Now in this case, you might want to run it as 4.1 because it really doesn't matter. So I'm going to go switch over to 4.1. To do that, I'll go to File, under Options, switch that over to 4.1, which is quite stable and had good results. Go back in there, go rerun it, and now it'll run with version 4.1. No errors here. So HEC RAS still has issues with it, and we report issues to them all the time on there. Anyway, so we've now run that. So if we want to go look at that structure again, we'll rotate that back around in a 3D view. We want to go look at that structure, go over to our results, go to a cross-section plot. So now if I zoom in, you can see here colorization of what's happening around that bridge opening. And so I want to see the velocities. I can click on one of these segments, and you'll just park your cursor there for a minute, and you'll see the velocities. So here it's almost 14 feet per second. So it's flowing around there pretty fast. What's going right here at the structure at the bridge pier? There we go. And that's 2.54. So it's slowed down quite a bit at that pier, right? So the darker colors, you can see it goes up to 16 feet per second. So something in here is 16 feet per second. That's 14. What's this one right here? 14. So somewhere in there, it's saying at least the plot is showing this. You can also sometimes, I think if you come in here, click on it, will it show it to you here? No, they don't have that option in there. Okay, so now we want to actually analyze our Scour. Now to get this plot, you may not find it right away. Again, we'll go to Options, and go to Velocity Distribution, and you just toggle this option on, turn that on. That's all you have to do. So now we've got our Scour, we've got our velocity distribution through there, so now we can compute the Scour. So go to Analysis and click on Scour Calculator. And we're using the standard HEC RAS calculator, okay? We're not changing it at all. But we're going to go ahead and analyze it. So we want to look at our 100-year storm. So I'm going to choose 100-year. Sometimes it reports that it can't load the results. So sometimes that won't load up. But let's see, I think it did. Yeah, it did. Looks like it loaded that one. Abutment. It did pull up my abutment stuff. Let's try the 25. Okay, we'll stay at 25 and figure out what's happening there for 25 for now. So we want to look at our contraction scour. So again, we have quite a bit of overbank flow in the right overbank looking in a downstream direction. Remember that? We're flowing down the river, looking at the river that way. And over on the far right side, we've got a lot of water coming through, right? And so we have to give it a, now in this particular case, we don't have to worry about these blank values. We have to put in our D50 size. Now if you don't know what a field is, if you click on the field at the bottom of the screen, or bottom of that dialog box, you'll see it says channel top width inside the bridge opening. So you can see it's reporting to you what these different fields are. That's the channel flow through the bridge opening. So in this case, we're going to look at our D50. It's saying fraction in millimeters. Okay, so that's a D50, 50% passing. And a typical value might be like, let's say maybe 2 millimeters, right? So we're dealing with some 2 millimeter particles, let's assume there. Then our K1 shear stress coefficient, go and look at that. our water temperature. What would be the worst case here? How warm would the water ever get in the summertime here? Right, so you want to consider that. Maybe 60 degrees temperature, that's probably reasonable. Right, depends where it is. If it's up in the mountains, it's not going to get that warm, but it calculates your K1. And it doesn't turn out that has a big impact. It doesn't change the value that much, but at least it tries to make it more accurate. Now for our piers, we'll come in there, change. You can apply it on a pier by pier basis, but most of the time all the piers are the same. But we're going to assume round nose piers. But if we want to really create a lot of scour, we'd want to go to square nose pier, right? So let's try that. Let's see what happens. We use a square nose pier. That's going to cause a lot of scour. And it's going to default to the Colorado State University equation. Notice the Froelich equation is not enabled by default. And if we go back to our contraction scour, you'll see it says equation default. So that default means basically it's going to look at those two equations, figure out which one controls, and use the appropriate value. So in this case, it's just going to go with, if I go back to pier, it's going to use the CSU equation. It wants to know for the CSU equation, what's the angle for that, the correction factor here. And I think I want to put 0 in for my angle. So it's just basically 1. If I bump that up, if I say the angle is 20 degrees, as you can see, it went up to 2.86. So it's actually going to take the scour and increase it by a factor of almost 2.8 actually. So we want to have a 0 angle in there. I don't know if you can leave it blank. I think you probably leave it blank. It still works. Then we want to go ahead and tell what kind of bed we have upstream of that. So I'm going to assume just a clear water. And then D95 passing, right? So basically 95% are smaller than that. So that's going to be a larger value than my 50, D50. So I'm going to assume like 5 millimeters. Let's see what happens there. And the Froelich equation is grayed out. We're not using that. Go over to our abutment scour. And you can see everything green here has been filled in. That's basically either from the analysis or from the data we've entered. It wants to have the skew angle in here. And it says 90 degrees is perpendicular to flow. So if we're angled perpendicular to flow, we want a 90 in there. And it's going to use the default equation. Again, look at the Froelich equation, the higher equation by Richardson, figure out what's going on. And we're going to go see. Now, to run this analysis, click on the compute button. And you can see the abutment scour got crazy, right? Sometimes I don't think I think somehow that equation's knocked out of whack there. So I'm going to try 45-degree angle on there just to see. We'll reduce that. We'll say compute. And you'll see it reduces it down. If I'm going to set it to 0, basically it's in line with that. We get no abutment scour. But you can see if we zoom in on this. If I zoom in, you can see now we can see our abutment scour. There's a little bit of abutment scour there, but we can see different types of scour. First thing it does, it calculates a contraction scour. You can see that little line there. You can click on this and it'll show us our contraction scour. Then it doesn't show it just shows the total scour. That's basically taking now the abutment scour and the pier scour and adding it on top of, superimposing that using superposition, applying that to our, lowering it basically on top of the contraction scour in there. All right, so I want to go and try out, we saw vertical abutment, right? If I choose a spill through abutment, let's change this angle so we get some abutment scour. So let's try, let's say 10 degrees, just see what happens for that if I hit compute. Okay, so that's 10 degrees scour, 10 degrees for abutment scour. If I go and switch this to a vertical with wing walls, it's going to reduce it from 1 to 80%, 82%. Right, so if I click on compute now, you can see it got reduced by, what is that, 18% or so. If I switch it over to spill through abutment, it reduces it by 45%. Right? If I click on compute now, you can see it's reducing some even further here. But again, I've had some issues here with this skew angle in here, so I don't know if they've got it hooked in there backwards or not. Because if you put in a, and you can, I think you put in a negative angle too. Let's see if we put in a negative angle. If I say -10, no. So of course it crashes right out if you put a minus sign. It dies out of there. Okay. But anyways, let's go ahead and try that real quickly. It should only take maybe 10-15 minutes maximum. If you guys can work on that example that we had yesterday, and we had this one here. And if you don't have a bridge pier in there, let's show you how you can put a bridge pier, and I'll show you how to put a pier in there real quickly. We'll just double click on it, brings up our structure. Now in my case I don't have a bridge pier, right? But let's put a bridge pier in. So you can use the little draw bridge pier, say add bridge pier, come in here, and I can just come in here and just click, right? It'll stick a bridge pier right there. Come down here, click it, adds a bridge pier, and then I can come and change these stations, right? I can come in here and change that to 1,000, so it's centered, and put in 1,000. So that's a fast way if you want to put in some bridge piers into your structure. Again, remember, do that velocity distribution, and then compute your scour. Okay? And I'll walk around the room to help you guys.